In our written response test, we have a compact car heading to the north at 10 meters per second and a full-size car heading to the south at 8 meters per second. Because we have a north and a south, they're two different directions. It's important for us to identify, to draw attention to the fact that we have two different directions so that we can remember later on to make one positive and one negative. These two cars collide head-on. Immediately after the collision, the compact car is moving to the south, and we don't know what the full-size car is moving. We just know that the interaction lasts 8.0 times 10 to the negative 2 seconds. We want to find the speed and direction of the full-size car. We want to show that it was inelastic, not elastic or inelastic, and we want to find the force and direction of the average forces of impact on both cars. Now, let's write down some givens here. D and E, of course, we're changing the question, so we'll worry about D and E later on. We'll focus on A, B, and C together here. What am I given in this? What am I given in this? Well, we know that the compact car, which we'll call car 1, has a mass of 1,000 kilograms. And we know that car 1 is moving initially V1I at 10 meters per second. It says it's 10 meters per second to the north. Now M2, that's my heavy car, and it's 2,000 kilograms. And we know that it's moving V2I at 8 meters per second to the south. We're going to make that negative 8 because it's to the south. We circled the negative sign, the south, to remind ourselves that there should be a negative sign in front of that, right? Now what else we got? It says after the collision, the compact car, so that would be V1F, has a velocity of 4 meters per second to the south. We circled once again the south there to remind ourselves that that should be a negative value. V1, the compact car, V1F is 4 meters per second. We also have a time of impact of 8.0 times 10 to the negative 2 seconds. The first thing we're looking for is V2F. Now this is a collision. This is a collision. And when we have a collision, the first thing that we want to think of is conservation of momentum. Pi equals Pf. Not some kinetic energy thing, not some impulse thing. Right? Impulse applies here, right, if we look at one individual object. But if we want to look at the system, and that's the easiest way to do this, then conservation of momentum is the way we go every single time. How many objects do we have before this collision takes place? 2, right? So we're going to say M1 V1I plus M2 V2I. Now, after they collide, how many objects do we have? 2. So we're going to say M1 V1F plus M2 V2F. They don't stick together. They don't entangle. If it doesn't say they entangle or stick together, then we have to assume that they do not. Now, it'd be nice if we had the same mass of these cars because we could cancel it if they did, but we don't. One is 1,000, one is 2,000. The only way we can cancel is if we have the same number in every term. So we're going to say 1,000 times V1I plus 2,000 times V2I. Don't forget the negative again. Negative 8 meters per second. M1, once again, is 1,000 kilograms. V1F is negative 4.0 meters per second plus 2,000 times V2F. Now, there's quite a bit here. I suggest that you do it in steps. If you're really good with your calculators, then do it all at once. But if you're making any mistakes at all, then don't do it all at once. Do it in steps. 1,000 times 10 is 10,000. 2,000 times 8 is 16,000. But we're going to subtract it because it's a negative value. 1,000 times negative 4 is negative 4,000. And we're going to add to that 2,000 times V2F. Let's combine these. It gives me negative 6,000 equals negative 4,000. Now, if I was doing this, I wouldn't show quite this much work. If you're really good at it, you don't have to show this much work either. But if you struggle at all with rearranging, then show every step. Take the 4,000 over by adding. I get negative 2,000. And we solve for V2F, and it works out to be negative 1.0 meters per second. You can leave it there. Negative 1.0 meters per second would be fine. Or you could also say 1.0 meters per second to the to the south. Either one of those would be fine. What you don't want to say is -1 to the south, because that would mean to the north, right? Good. Question A is done. If you got that, you get 2 points. B, show that the collision was not elastic. Show that the collision was not elastic. Well, to determine whether something's elastic or not, if they stick together, we know it's not elastic, right? There's nothing we have to do then. If they stick together, like, it has to be inelastic. But if they bounce apart, it's probably still not elastic, but it could be, so we got to check. And this is how we check. We calculate the initial kinetic energy, not the initial kinetic energy of one object, but the total initial kinetic energy. 1/2 m1 v1I squared plus 1/2 m2 v2I squared. This is 1/2 of 1,000 times v1I was, what was it, 10, I think? Plus 1/2 of 2,000 times the initial speed of the second car, v2I, is 8 meters per second. Why did I drop the negative there? Like, I was so insistent that you circle the negative or circle the south to make sure that we remembered it's a negative, and now I'm not including the negative? Because energy is a scalar, right? Momentum's a vector, we need the sign. Energy is a scalar, we don't need the sign. In fact, not only do we not need it, we don't want it. When we do this, I believe it works out to be 1.14, or technically I guess it should be 1.1 times 10 to the 5 joules. I don't have my answer key in front of me, but I'm pretty sure that was right, isn't it? Yes, 1.1 times 10 to the 5 joules. All right, good. There's the initial kinetic energy, not of one object. That's not what I want. The initial kinetic energy of both objects combined. And then we got to do the final kinetic energy. It's 1/2 m1 v1 f squared plus 1/2 m2 v2 f squared. So 1/2 of 1,000 times, what was v1f? 4 meters per second. Although we dropped the sign. Plus 1/2 of 2,000 times, what was v2f? We just found it, 1 meter per second. We do the calculation there, and I think it worked out to be 9.0 times 10 to the 3 joules. What do you notice about those two kinetic energies? They're different. You lost kinetic energy. In fact, you lost a lot of kinetic energy. So we would say that since we lost kinetic energy, or since EKI is greater than EKF, it's got to be inelastic. Say it any way you want, but basically make sure you recognize that if you lost kinetic energy, it's got to be an inelastic collision. C. C asks us to determine the magnitude and direction of the average forces of impact on both cars. I want to do one car at a time, and I want to use impulse for this. I've got a time, and I want to find a force. Force and time always lead us to impulse. Force and time lead us to impulse. So I'm going to use the equation for impulse as it appears on my data sheet. F times delta t is equal to m times delta t, m times delta v, I should say, for the compact car. That means F for the compact car is m delta v over t. The mass of the compact car is 1,000 kilograms. Delta v, not v, mv would be momentum. M delta v is impulse. And delta v is final minus initial of the compact car, car 1. The final was -4. The initial was 10. So we're going to say -4 minus 10. Final minus initial velocity for the compact car. And the time of impact was 8.0 times 10 to the negative 2 seconds. When you do this, it works out to be, I believe, negative 1.8 times 10 to the 5 newtons. Or you could say 1.8 times 10 to the 5 newtons to the south. Car is moving to the north. When it gets stopped, the force that stops it is to the south. Now, if you want to do the full-size car, which you want to do here because you're asked to find the force on the full-size car, we would say m times delta v over delta t again. The mass of the full-size car is 2,000 kilograms. The final velocity of the full-size car was, what was it? -1 or 1 to the south. The initial velocity was -8 or 8 to the south. So -1 minus -8 over 8.0 times 10 to the -2. So it becomes 2,000 times -1 plus 8, right? Negative plus. When we do this, it works out to be, would you look at that, 1.8 times 10 to the 5 newtons. If you get the same answer there, like if you get those two numbers the same, like that's gotta, like that, a light bulb has got to go off in your brain thinking there, like, I must have done something right. Like, even if you didn't recognize ahead of time that they should be the same number, like something's got to click there that I must have done something right. Now, you could have just solved the first one and then said, second one's equal and opposite, right? Because if object A applies a force on B, object B applies an equal and opposite force on object A. So you didn't really need to do the second calculation if you remember Newton's third law in that instance. But you still could, and obviously you still get the right answer if you do. Nice little check if you do, right? Because if you get the same answer, like, you got to be right. Now, let's go back to D. D and E are a little bit different. They change the question a little bit, turn it into a two-dimensional problem. Now the full-size car is going west, and the northbound compact car still going 10 meters per second. They collide and they stick together. So we got a situation like this. We got in question D the full-size car going west. That's going to be car number 2 with a mass of 2,000 kilograms. We've got 8 meters per second. And we've got the compact car, car number 1, that has a mass of 1,000 kilograms going to the north at 10 meters per second. They're going to stick together and go off this way. X and Y components, right? Funny, like some of you guys did a better job on this than you did on question A, actually. PI equals PF. We're going to say M1V1I plus M2V2I, 0 plus 2,000 times -8. Why 0? Where's the 0 come from? Object 1 isn't moving on the x-axis. Object 2 is moving at -8 on the x-axis. Equals, they stick together, 3,000 times VF. And VF works out to be, I want to say it was 5 point something, wasn't it? Does anybody have that? -5.33, -5.33. Now we do the y components. We'll say 1,000 times 10, m times v, plus 0. Why 0? Because object number 2 is on the x-axis and we're doing y. Equals 3,000 times VF. Almost done here, guys. Almost done here. We solve for VF there, and it works out to be 3.33. So we draw this. We redraw this. -5.33. Positive 3.33. We do the Pythagorean theorem to get the value of V, and we use the inverse tan function to get the value of theta. V works out to be 6.3 meters per second, and theta works out to be, by the way, guys, let's leave. If you're leaving, I'll just get you to leave your tests here, okay? If you're leaving, I'll get you to leave your tests here. Theta works out to be 32 degrees north of west. And finally, question E. Question E asked us, without calculations, how do you know that this collision was not elastic? Because they stuck together. Now, a couple of people wrote something that I didn't anticipate, and I marked it right, actually. They said, well, the speed of both cars is less than it was before. Well, okay, you have to lose kinetic energy then if the speed of both cars is less. That's not what I was looking for, but I couldn't really say no to that because you didn't do a calculation and you still recognize that it had to be inelastic. I was looking for the fact that they stick together.